Alright, in this video we're going to try to combine some of the ideas of equilibrium constants with acid-base reactions. So the first thing we need to talk about is something called Ka. It is called the acid dissociation constant. It is also sometimes called the acid ionization constant. It is exactly the same thing. There's no difference between these definitions, but some textbooks call it one thing and some textbooks call it the other, and I'm not sure which way Sapling phrases it. It's Ka though. It is literally exactly the same thing as Kc. So it's Kc for the reaction, but it's a specific type of reaction. It's Kc for the reaction of a weak acid dissolving in water, or dissolved in water. But literally, it's product of reactants raised to the coefficients. It just applies to a very specific reaction. Okay. So for example, acetic acid. May not have seen this since last semester, but has a Ka of 1.8 times 10 to the negative fifth. Doesn't really matter if it's a big number, low number, whatever. This is all the information that you might get on like a quiz or exam. What you're supposed to extrapolate from this is that the reaction looks like this. Because this is a Ka, we're assuming this is an acid. There's something called Kb we're going to learn about like in 5 minutes. Okay. And what's happening is it's this acid reacting with water, which I'm going to label as a liquid for this particular example. This is going to be aqueous. And it forms an equilibrium because we have an equilibrium constant. And what happens is this is going to act as the acid, and this is going to act as the base. It's not critically important that you realize this, but for acetic acid, this H on the far right is actually the one that gets popped off. Organic molecules look a little weird sometimes. So what happens is this thing's going to lose an H+, so it'll be CH3 COO minus, because it was neutral and we lost a plus charge. And this thing is going to gain a plus charge, so it'll become H3O plus. Hey look, hydronium ion. We're going to see that a lot. Okay, so this was the acid. This is the conjugate base. This was the base, so this is the conjugate acid. I'm going to be abbreviating conjugate like that pretty much every time. Sorry. So, oh yeah, I guess this is, since we're writing aqueous and liquids and all that stuff, these are all aqueous. So, if we were going to write Kc for this reaction to be products over reactants, that's exactly what this is. It's literally just Kc for this specific reaction. So, Ka is concentration of CH3COO minus times concentration of H3O plus divided by the concentration of CH3COOH, and we can ignore the water because it is a liquid. In the last chapter, we talked about the idea that anything that is a solid or a liquid does not get to be included as part of the Ka. This actually is going to save us a lot of headache because this type of reaction happens like every freaking day for the next couple chapters. Being able to ignore one of the four things is pretty useful. And it turns out that because we have the value, that this is equal to 1.8 times 10 to the negative fifth. And honestly, we could basically do equilibrium style problems based off of this. All of this bit is implied from this. Because it is Ka, it explicitly implies this exact type of reaction. We're assuming this is an acid, and we're dissolving it in water. That's what Ka means. And then you get the conjugate base and the conjugate acid. Okay, so basically the CH3COOH is the acid. It's going to lose a proton and become the conjugate base. Water is going to be the base. It's going to steal a proton and become the conjugate acid. And it's products over reactants raised to the coefficients. I can't tell you that we won't ever have coefficients in the front, but honestly, these Ka and Kb values are almost always ones in the front, so the exponent part really doesn't come up very often. It actually makes life a little easier. In terms of interpreting Kas here, the larger the Ka value, the stronger the acid. Probably should have just underlined the whole thing, but you know, whatever. So if we had another acid and it had a Ka of like 9.5 times 10 to the negative fifth, we would know that it's a stronger acid without having to do all the legwork here. We can literally just look at the Ka value and tell you whether it's a stronger acid or not. Okay. There is a completely analogous version of this for bases. So let's do that real fast. There is the base dissociation constant. And hopefully it's not too surprising that this is Kb. Again, this is sometimes called the base ionization process. Oops, ionization constant. I guess I didn't point it out up here. This is what happens when this thing breaks apart into the molecule and the H plus come off, which is why it's called dissociation. It's also called ionization because things are molecules splitting into ions. Either one is acceptable. The same thing is going to happen for bases. So I guess I'll rewrite this definition, even though it's almost exactly the same. So Kb is essentially the same thing as Kc. It's products over reactants raised to the coefficients for a reaction of a weak base dissolved in water. Nothing new here. Exactly the same idea. Okay? So we had a molecule in a Ka value. NH3 we said was a base. It turns out it's a weak base, and its Kb value, by pure coincidence, is also 1.8 times 10 to the negative fifth. Honestly, all this means is this is exactly as good of a base as this is an acid. It is pure coincidence that these things have the same number. Not every Ka and Kb are 1.8 times 10 to the negative fifth. Okay. Again, you would be given this much information, and it is assumed that you could extrapolate to give this type of balanced equation and such. So, essentially, NH3, we said, is going to be a base. It has a Kb value. Okay, and it's dissolving in water, which I'm going to label as liquid. The other ones are all aqueous. It's because this is a base, it's going to steal an H+, so we're going to end up with NH4, and this is going to lose an H+, it's going to be an OH-. So because this was a base, this is the acid. I'm trying to keep my colors consistent. Because this is a base and it picked up an H+, this is now the conjugate acid. And because this was an acid, this is now the conjugate base. And Kb for this particular equation is products over reactants, so it's concentration of NH4 plus times concentration of OH minus divided by concentration of NH3, and again, we ignore the water because it is a liquid. Okay, and it's equal to 1.8 times 10 to the negative fifth. And we set up here that the stronger the Ka value, the stronger the base, or stronger the acid. Same thing down here. The larger the Ka, or God, I keep mixing them up. The larger the Kb value, the stronger the base. Sorry, my handwriting gets, these markers are kind of sloppy. Okay. So let's talk a little bit about strong acids and just for comparison's sake. Okay, there's a lot of stuff on one page, sorry. So if we had something like HCl, okay, it turns out that HCl is a strong acid. If you dissolve this in water, which is a liquid, water will act as the base. Because this is a strong acid, it'll rip that H+ off and we see a Cl-. We saw this literally as like the first reaction on the last video. The reason it is a strong acid is there is no reverse reaction. Strong acids only go forward. But you still get an H3O+ and a Cl-. So this was the strong acid, so this is its conjugate base. This was the base, this is its conjugate acid. Okay. It turns out that the stronger the acid, the weaker its conjugate base is going to be. Okay? So because this is a very strong acid, this is a really terrible base, which makes sense because if this is a really bad base, it's not going to react and go backwards. Okay? So I'm just going to label it as a terrible base. Whereas if we compared that to acetic acid, so CH3COOH plus H2O, this would be reversible. And we get H3O plus, CH3COO minus, nothing we haven't seen. I'm going to relabel everything. This is a weak acid, and this is going to be a base again. So this is a conjugate acid, just like we already saw, and this is going to be the conjugate base. Because this is a weak acid, this is going to be reversible. And the reason it is a reversible reaction is this is an acid, and this is going to be a half-decent base. I'm going to label it as a pretty good base. I know that's pretty vague, but... And because this is a half-decent, pretty good base, it will react with the acid and make the reaction go backwards, which is why we get the reversible reaction. So because this is a terrible base on the first one, there's no reason for it to go backwards, so we don't get a reverse reaction. So I'm going to summarize some of that here. The stronger the acid, the weaker its conjugate base. Okay. And similarly, for the exact same reason, the stronger the base, the weaker its conjugate acid. Okay. Let's talk a little bit about strong acids and strong bases. I'll probably finish out this video with this. Okay. I am just going to give you a list of all the strong acids that there are. There's only 1, 2, 3, there's 7 of them. I'm just going to ask you to learn this list. Okay, so there are 7 strong acids. I need you to memorize this. Okay. 3 of them are almost the same thing. So HCl, which was the example we saw up here, it turns out that anything in that column all kind of behave the same. So HCl, HBr, and HI do that. Turns out that HF is a weirdo and it doesn't play that game like that. Okay. The other ones are mostly the acid form of polyatomic ions. So it turns out that HNO3, nitric acid, is a strong acid. HClO3, this is perchloric acid. Remind me in class and I'll tell you a story. I dissolved a turtle once with this. It was dead already, but it was for research. I'm not just creepy. Oh, actually, I lied. HClO4 is perchloric acid. This is chloric acid, this is perchloric acid. And H2SO4. These are like the 7 main strong acids. So what I'm going to tell you is that if you're ever in the real world and you need a strong acid, it's almost easier just to memorize this list than it is to like learn the complicated nuances of why one is a stronger acid than the other. Okay. Honestly, what it has to do with is the ion that comes off, the conjugate base, is really, really stable. Like NO3 has resonance structure, Cl, honestly, all 4 of these ones have resonance structures, and Cl, Br, and I minus all are all really, like when we did our solubility rules last semester, they were all stable as negative ions, which means the H plus can pop off and there won't be a reverse reaction. Okay. Strong bases are even easier. Basically, if you have a soluble salt, so in other words, a salt that will dissolve in water with OH minus as the anion. So if you have NaOH or KOH or CaOH, whatever, anything with an OH minus as the anion, if it will dissolve in water, it'll be a strong base. So that's really, really easy. Okay. So let's kind of try an example of some of this stuff, just so that you have an example in your notes. So let's say we have 2 acids, HF and CH3COOH. Can't write legibly, sorry about that. And the Ka for HF is 6.6 times 10 to the negative 4th. and the Ka for CH3COOH is equal to 1.8 times 10 to the negative fifth. We already saw that. Okay? So based off these Kas, which one is the stronger acid? Well, at the bottom of the last page, well, middle of the last page, basically the larger the Ka value, the stronger the acid. 10 to the negative fourth is larger than 10 to the negative fifth. This is the stronger acid. Okay? Let's try this. F minus versus CH3COO minus. Which one is the stronger base? I guess I'll separate these a little bit. Well, we said the stronger the acid, the weaker its conjugate base. So because this is the stronger acid, F minus is its conjugate base, this is going to be the weaker base. So because this is the weaker acid, this will be the stronger conjugate base. Okay. A little weird, but we did technically address all these things. All right, thanks.